Hello, my name is Emidio, and I would like to talk to you about my project about actuators in the hip exoskeleton. As you can see, the hip exoskeleton consists of three parts. The motor, which consists of the electrical part and the mechanical part, the transmission, and the torque output. As you can see in this image, we have multiple equations that are in time domain. To make our calculations easier and our simulation tests a lot more faster, we convert these time domain equations to a frequency domain equations. This is done by using the Laplace transform. In my project, I would compare two actuation paradigms, the series elastic actuator and a quasi-direct drive actuator. As you can see, a series elastic actuator has a low bandwidth, but a medium type of bike drivability. Compared to the quasi-direct drive, it has both high bandwidth and high bike drivability with low mass. So what's bike drivability and what's bandwidth? So bandwidth measures how fast a signal responds to a changing input command, while bike drivability is the level of easiness of the transmission from the output to the input axis of movement. So meaning high drivability equals to low resistance force. These are very important factors when you want to design a hip exoskeleton. So to start a simulation, we first have to draw the block diagram for the bandwidth and for the bike drivability. As you can see, our transfer function would be dependent on the torque that is outputted versus the reference, where one n is a feedback. And for the bike drivability, due to the fact that we are comparing to an unpowered source, our voltage would be 0. So our input would be depending on the leg position or delta H. As you can see through the transfer function below, it will be consistent of the torque output divided by the leg position or delta H. To run this simulation, I inputted these type of parameters. As you can see, each actuator consists of different parameters. And this is the Simulink code for the bandwidth. For the input, I inputted amplitude of 3 Newton meters of a hertz ranging from 0 to 300 hertz for a simulation time of 30 seconds. In this, after the simulation ran, we can see that the QDD or the quasi-direct drive has a higher frequency compared to the series elastic actuator. This means that the QDD actuator can keep up during a regular gate cycle much more efficient compared to the series elastic actuator. This makes it much more beneficial for the user. In this image, it shows the Simulink code for the bike drivability, where the input function is 0 to 1 hertz for a simulation time of 5 seconds and an amplitude of 5 degrees. In this plot, you see that the QDD has a higher bike drivability compared to the series elastic. This is shown due to the fact that the quasi-direct drive has a lower frequency resistive torque compared to the series elastic. This means that the user will use less force to push the mechanism back to its normal gate cycle. Now I would like to talk about the overview of the class. Due to the pandemic that was going on, that recently goes on as of today, we were forced to do an online course. Through to this online course, I was able to learn a lot more about MATLAB and Simulink. This is my first time exposed to Simulink, and it kind of helped, and I really am grateful that I learned Simulink, so in which it can help me find certain positions and do simulation tests when it's required. Thank you, and I hope you enjoyed the video.